awful power of the atom was first released as a bomb, a startled world asked itself, what is this great new force? What terrible secret has science uncovered? Actually, knowledge of atomic forces is not new, and although the work being done on the atomic bomb is subject to strict security precautions, there is basically no secret. Now, as for thousands of years, scientists are seeking an understanding of the ultimate structure of matter. A search which began to crystallize early in the 19th century with the work of men like John Dalton. Dalton held that each element was made up of atoms which were all alike and differed from those of other elements. He invented a system of symbols to represent the atoms of different elements. By 1869, Mendeleev fitted together a fairly complete picture of the elements. The properties and places of unknown elements were predicted. The discoveries of later years proved the accuracy of the forecasts. With the discovery of electrons, the realization of the nature of positive rays, and the study of the properties of X-rays, a revolution occurred in the conception of the nature of matter and of the atom itself. The study of radioactivity, first investigated by Becquerel and then by the Curies, revealed the complex nature of the rays that are constantly emitted by these substances. These rays behave in a peculiar way in a magnetic field. A fairly weak magnetic field produces a deflection of light-charged particles called beta rays. A strong field causes further deflection of beta rays and a deflection in the opposite direction of heavier charged particles, alpha rays. There remains a penetrating radiation not affected by the magnetic field, the gamma rays. Alpha rays consist of positively charged helium atoms. Beta rays consist of electrons. Gamma rays are electromagnetic waves similar to X-rays. Furthermore, radioactive elements undergo spontaneous changes. Uranium, for example, gives rise to a series of unstable elements. The rate of change from one element to another may vary from a fraction of a second to millions of years. But finally, uranium becomes completely transformed into the stable element lead. Thus, some elements can change their identity. This fact led Lord Rutherford to make a great advance in atomic theory. He suggested that the atom is composed of a small nucleus around which revolved electrons. By 1932, scientists could say with certainty that the atom contained electrons carrying unit negative charges and a nucleus built up of protons carrying unit positive charges and of neutrons, uncharged particles equal in mass to the proton. To understand what happens when the structure of the nucleus is changed, it is necessary to recall that in 1905, as part of his theory of relativity, Einstein made the startling statement that mass and energy are different forms of the same thing, and expressed this idea in his famous formula, E equals mc squared. In this formula, E is energy, m is mass, and c is the velocity of light. It says, in effect, that a small amount of mass can be converted into a tremendous amount of energy. In 1932, Cockcroft and Walton found it actually possible, by bombarding atoms with particles at high speed, to split their nuclei. When the lithium nucleus was struck by a proton, it split into two helium nuclei. When this occurs, a small amount of mass actually is lost, with the release of a great amount of energy. Great machines have been constructed to produce streams of high-speed particles to bombard and smash the atom. One of the most famous of these is the cyclotron, invented by Professor Lawrence of the University of California. In a vacuum tank, which is placed between the poles of an electromagnet, are two hollow D-shaped electrodes to which a high-frequency alternating voltage is fed. Minute quantities of gas furnish the bombarding particles. Electrons emitted from the center of the tank by a small arc or filament ionize the bombarding particles. The particles are sucked into either one of the two Ds by the powerful electric field. Since this movement takes place between the poles of a huge electromagnet, the particles travel in circular paths. The alternating voltage accelerates them each time they cross the gap from one D to the other. They are whirled around faster and faster until finally they are let off at tremendous speeds by a charged deflector plate. Here, an element is being set up in the target chamber, ready for bombardment. It is now known that almost all elements, if bombarded by neutrons, can be made radioactive. The scientist must operate the cyclotron from behind a screen of water several feet thick to protect himself from the intense and dangerous radiations. Through the observation window, the pulsations of the particles can be seen around the glowing arc. Some idea of the neutron's effect on the nucleus can be given by this simple demonstration. Imagine that the saucer is the nucleus of an atom. One might think that the neutron would go straight in and out the other side, like this. Now the saucer is filled with marbles to represent the particles of the nucleus. If the neutron marble rolls down into the nucleus, it jostles the others but remains in the saucer. It becomes unstable and gives off its excess energy as beta and gamma radiation. If the neutron marble enters the saucer with more energy, one or more marbles will be knocked out. Thus, neutron capture can eject particles from the nucleus, causing disintegration. Uranium is unstable, as shown by its ability to emit an alpha particle. When the uranium nucleus captures a neutron, it becomes even more unstable. Then, fission occurs, the nucleus splitting into two nearly equal fragments. Great amounts of energy are released in the process, and the fission fragments are hurled apart with tremendous velocity. If each fission has to be produced by elaborate apparatus such as this, there would be no hope of deriving useful energy from the process. But each fission is accompanied by the release of a few neutrons. One neutron started the fission. The fission itself produces more than one neutron, and is thus itself capable of causing more than one fission, and so on. The result is a self-sustaining chain reaction. Even the first fission-provoking neutron does not have to be supplied from outside, since a few fissions are always taking place spontaneously. These supply the necessary neutrons. Such a fast chain reaction is the basis of an atomic bomb. There are two isotopes which make up the bulk of natural uranium. The atomic weight of one is 238, the other 235. Over 99% of natural uranium is U-238. U-238 undergoes fission only with very fast neutrons. Many neutrons are scattered by uranium atoms and lose the speed necessary to cause fission. Therefore, a chain reaction will not take place in uranium, which is predominantly U-238. U-235, on the other hand, undergoes fission with neutrons of any velocity, but is most likely to capture slow ones. A controllable chain reaction is obtained by using slow neutrons to cause fission in U-235. To achieve this controlled chain reaction, a pile is built. Pure uranium rods containing both isotopes are embedded in a mass of pure carbon in the form of graphite. Neutrons produced in the uranium are slowed down by collisions with the light atoms of the carbon, the moderator as it is called. These slow neutrons are captured by U-235, which then splits. The first controlled chain reaction was achieved in 1942 at the University of Chicago. If natural uranium and a moderator are replaced by a small amount of U-235, slow neutrons instead of fast ones are produced. Fissions take place, but so many neutrons escape without hitting a nucleus that no chain reaction is built up. But if the amount of U-235 is larger than a certain critical size, a fast chain reaction takes place in less than a millionth of a second. This results in a violent explosion. In principle, therefore, an atomic bomb works like this. Take two pieces of U-235, each smaller than the critical size, but which together exceed that size, drive them together, and thus U-235 is a key material for the atomic bomb. The behavior of U-238 in a pile is also of great importance. Slow neutrons are sometimes captured by U-238. No fission occurs, but this nucleus becomes U-239. This is unstable. A beta particle is emitted. A new element is formed, Neptunium-239. This new element is also unstable. Another beta particle is given off, forming another new element, Plutonium-239. Now, plutonium has fission properties similar to U-235 and is built up by this process throughout the uranium in the pile. Since it is a different element, it can be separated from the uranium and used also for a bomb. So, plutonium is the second key material for an atomic bomb. The actual processes involved in obtaining materials and constructing a bomb are done under strictest security regulations. It is costly work and dangerous work. Elaborate precautions must be taken by workers on the atomic pile and in the laboratories because of the danger of the deadly radiation. Danger signs and warning signals, lead and concrete shields, remote controls, detectors, protective clothing. These are commonplace to the men who make material for the bomb. In the desert of New Mexico, the first atomic bomb was set off. Thousands of calculations, years of work reached their climax in this moment of deadly splendor. Within a few weeks, the bomb burst over Japan, and the news of it upon a startled world. Since then, this weapon has been made even more powerful. The knowledge of how to unlock the atom is a grave responsibility. Another war, and civilization might die, just as Hiroshima died. A city destroyed in an instant, many tens of thousands killed. This destruction makes us fervently hope that atomic power will never again have to be used as a destructive force. Although work on the bomb continues because of world tensions, constructive uses of atomic energy are also being developed. One way of harnessing atomic energy will be to turn the atomic pile into an efficient heat engine. The release of energy in a pile results in the generation of heat. If the reaction is allowed to run fairly fast, a cooling system is necessary. To control the rate of the reaction, rods of cadmium or some such substance must be introduced, which can absorb neutrons if lowered into the pile. Now, if a cooling substance, possibly helium gas, were passed through a heat exchanger containing water tubes, the water could be heated and turned into steam. Most of this part of the installation would have to be screened off by heavy concrete or water shields and operated by remote control. The steam could be used to drive turbo generators to provide electricity in a powerhouse or in a large ship. This adaptation of the atomic pile as a source of heat energy is now being tackled. Many important uses of radioactive byproducts from the pile have already been made. Medical research is now employing new tracer techniques based on radioactive elements. In this test, a radioactive sodium salt is being used to check blood circulation time. The Geiger counter picks up the radioactivity from the sodium. Now the doctor prepares to inject the sodium into a vein in the patient's foot. The radioactivity will be picked up by the counter as the sodium in the blood reaches the patient's groin. The injection is made, and the scientist starts his stopwatch. Absorbed in the bloodstream, the radiosodium travels up the leg. The counter is shielded from outside radiation by the lead block with a slot beneath. Now 10 seconds have passed, and the counter reveals the arrival of the radiosodium. From such experiments come many useful facts which add to our knowledge of the body's behavior in health and disease. For many years, scientists have been studying the vast amounts of energy produced by atomic explosions in our sun and in the stars. Under conditions of tremendous heat and pressure, complicated nuclear reactions occur, resulting in the building up of helium nuclei from hydrogen. In this process, which is the reverse of nuclear fission, mass also disappears. This results in the release of even larger amounts of energy. This power from nuclear fusion is the basis of the hydrogen bomb. The energies now within our grasp are tremendous. But we must learn to control not only these physical forces, but also the human forces of greed and hate which bring about wars. Only then can we use our power wisely and realize a future of great promise.